It should be another graph physics video production. Presentation. I keep forgetting. But anyway, I'm not producing much. I mean, I'm not actually creating the video ahead of time. Mixing the ingredients, just handing them to you. Anyway, comments first, and then maybe something on drag. Yeah. It'll be so full of drag. Anyway, I saw Ken Wheeler sitting on a panel at a lecture with Eric fucking Dollard. Okay, yes, it's the free energy convention. Okay, tinfoil hat all over the place. Shyster all over the place, all selling their perpetual motion machines. Their perpetual battery. Just press the button, it makes energy forever. Fine, whatever. Funny you were not on said panel. Why would I be on said panel? It's not about the truth. It's about a bunch of shysters trying to bilk people out of money. So why would I be on that panel, idiot? All right, anyway, his point on your gyroscope rant. No, I'm not the one ranting about the gyroscope. It's Ken Wheeler ranting about how the magnetic field is less magnitude. The bigger the magnet, the smaller the magnitude. Blah, blah, blah. He's the one ranting, okay? Making bold claims he backs up with no evidence. You do the experiment yourself. Stand 30 feet away from an old TV and prove that your magnet is weak. That doesn't obey Maxwell's laws, which they're not really a recitation of a law. Maxwell didn't make laws. He just described phenomenon in a sense that he put two and two together. These variables control these outcomes. And that stuff's pretty established. The inverse square law, the way light travels. There's no light bulb that has less magnitude. It doesn't happen. You can't have a brighter light bulb with less magnitude. Alright, idiot. Fucktard. Okay, anyway. His point on your gyroscope rant, there's no point, okay? It's nonsense. Is when mainstream science, well, why doesn't he show us mainstream science doing the experiment? It's really easy to do. There's millions of videos on YouTube, tons of professors doing all kinds of stuff. Why doesn't he point out one of the show right there? Look, I did the experiment and I have completely different results. Why don't we see any of that? Oh, that's right, because then none of that ever happens. Nothing they're saying is inconsistent with what Ken Wheeler is demonstrating. Not a single thing. Alright, anyway, science puts a Gauss meter at the center. Well, where do you have evidence of science doing that? Is some idiot somebody doing that? A Gauss meter is what? A little magnet on a stick. We already know how the magnet's going to line up. We already know how, if you put it in on the north side of the magnet, that is, where the south side can't get to it, that it's in a different field than it is when you put it on the edge where the south side can get to it. You're diluting the field. Conventional science probably would have no problem saying something like that. Anyway, it puts the Gauss meter in the center and the edge of a magnet. It does not define a magnet. Well, whatever. So again, this argument that somehow the field lines have been well established in the sense of the fact that there's proportionality at certain distances and the intensity of the field. I've already pointed out that there are no such thing as field lines. They're completely arbitrary. All there are is lines of force. As Faraday put it, straight line force. His gyroscope proves, so here we go again. You prove something? No, you didn't prove anything, silly person. Magnets are way more complex than science knows, so there's no complexity. A compass needle moving is complexity? Boy, are you ever deluded. And again, there's no evidence it moves in any other way than the standard way. Just like the ferrocell. The ferrocell, all the little filings are lining up just like they would if they were little iron filings on a piece of paper. Nothing different is happening, and the only thing you've changed is you've decided to angle it. You've decided to reflect light off of it in a specific way to try to make it look like it's something else. So there's no proving anything. You're just another shyster selling crap, okay? Selling gimmicks. proves magnets are way more complex than science knows. Well, they clearly don't understand how magnets work, conventional science, but either does Ken Wheeler. Ken Wheeler is even more silly and stupid. Right? Science has already got something very simple. They've complicated it by creating waves and all kinds of other nonsense that don't exist. But you people are even sillier with your silly hyperboloids and your toroids that you can never find. Do an experiment showing me the existence of this silly nonsense, because it doesn't exist. There's no evidence of any static magnetic movement. Okay, static magnets don't have anything moving except just like a light bulb. Little rays are coming out of it. Idiot. As the Gauss meter does not show shit. So again, more nonsense. Of course it shows plenty. Okay, the magnet on the edge of the magnet, it tips. It goes sideways. It doesn't point straight up anymore. Jesus. So silly. Too fucking stupid. V darkness, whatever that means. V darkness falls. Well, you're all such special characters, right? You're like little Pokemon characters or something. Ugh, fuck. Alright, superior mind. Your explanation of polarization filters via phase shifting and pattern electron emission makes perfect sense. I don't know if I'd say it that way, but yes, the electrons make the photons, and they're the ones imposing the polarization on the photons. And yes, my explanation that polarization just has to do with a lack of perfect consistency in the plane of the quanta. Alright, yeah, see, there really isn't a great way to say it, not off the top of your head anyway. That electrons don't shoot photons perfectly straight. Perfectly straight. The gun moves as the electron's firing. And the fact is that all you're changing is the position of the quanta by putting it through a filter. The ones that are more out of alignment have their phase changed. But the energy goes right through the filter. And you can get it back again. You can get the photon back. Easily understood. Brilliant. Yes, of course. So you think so. I have a bit more work to do to get the morons to get it. So anyway, Chris Russell, whoever he is, another nothing account. Jesus Christ, you gotta stop watching. I gotta stop watching this now. Oh, it's too much for you. And you won't make a counter argument that has any kind of substance at all. Because this guy is a moron. Yeah, I could write that on any video on YouTube. Doesn't mean a damn thing, does it? Oh, the anonymous coward says so. Oh, so fucking impressed. Old Aphora, whatever that is, might babble on and never get directly to the point. Oh, well, that's not at all important, right? When it comes to a discussion about physics or how something works. Oh no, that might be important. But this guy just ... Oh, the mystery, non-existent. You could quote a piece of it. I mean, I can almost say hyperboloids and toroids and increase the power, decrease the magnitude. I can say crap like Ken Wheeler. I can quote him, and it's bullshit. Stupid in biblical proportions. No, it's Ken Wheeler who's dragging up the long dead and say they had all the answers. So even though they were basically covered in, bugs, they had all the answers. They hadn't invented a nice, clean, sanitary bathroom yet, but now they had all the answers. I'm still waiting for someone to explain how the magnetic field escapes the iron core to cut the conductor, forming the secondary. So all this cutting crap is just crap. I mean, it's basically an engine that needs... it's like fuel in a gasoline engine or something. They have little nozzles on it, so it spreads the fuel like an oil burner or something. Because that's the only way it's going to really work. It has to create heat, and you have to give it the opportunity to change the environment for the other molecules so they heat up, and then that creates more capacity for you to create a combustion chain reaction. So there's certain rules to lighting a fire, for example. There's just rules. You have to obey the rules. And so there's rules about magnetism and electricity. And I would argue the simple rule you can understand sort of is that when the electricity is flowing through the wire, it's changing the atoms, right? So when electricity is going from point A to point B, what you want to do is change as many atoms as possible on that path, because as it's changing the atoms, it's making them into magnets. And the more little magnets you make, the more magnetism you have. So for you to create magnetism, you have to change the atoms. And so if you understand it in that simple context, you can understand that if you spread, okay, the force, you're going to involve more atoms. And as you involve more atoms, that is, create lots of little currents rather than one big current, you'll create more magnetism. And that's what you're trying to get out of your electricity. So it's really just about changing the path the electricity takes. The more path changes you make, the more magnetic effect you get. That's why you use high amperage. When you're just using straight wires and you want to make them attract or repel, you put a ton of amperage in, because the higher the amperage, the more atoms you're involving. The higher the voltage, the fewer atoms you're involving. So, but you're too stupid for this conversation, so I'm just probably wasting my breath on you in particular. I'll just assume you have some doppelganger, in the real world, some other asshole who wants to type shit like this that might actually be listening, and so I'm really just talking to your moron twin before he shows himself to be a moron. All right. Escapes the iron core to cut the conductor forming the secondary. Again, there's no cutting of a conductor. You're just transferring something. You're transferring a force in one form, and you're creating a phenomenon in another form. All right? But you still have to have the force for that phenomenon to mean anything. So as I've pointed out, it's really just about creating mirrors. So I've turned on the light, and the light has this funny property where it turns, wherever it hits, it turns it into a mirror, and then the photon stays. And so the more mirrors I make, the more atoms I change into a mirror, the more I'm going to keep all that energy in here. And that's really what you're trying to do, is amplify, magnify the magnetism, because then the magnetism will be pressure and it'll create more current. Yeah? All right, anyway. Yet somehow the conductor develops an EMF. Well, it doesn't really create any electromagnetic fluxes or any of that kind of crap. It's not happening. There's one force, okay, and it does two things. In atoms, it makes the pressure move from one atom to another. That's electricity. And when the atom pressurizes, it polarizes, which means it makes it into a little magnet. And if you line up all the magnets in the same way, that is, you have the currents all moving the same way, the transfer of the pressure, then you line up all those little magnets the same way, and you make a stronger magnetic effect, a stronger mirror. All right. In an air core, sure, magnetic lines go everywhere. Well, they really don't. So that doesn't mean anything either. It's just that the effect is you're seeing it. You're saying, oh, there's some field on the outside. It's just the proportions are so huge in terms of the magnitude. You change how much magnetism you can make because you've put a big giant piece of iron inside the core, and all of those atoms can now line up and become a magnet. So you're saying, oh, I'm surprised that there's this differential in the field when the core is in there, and then the differential doesn't seem to exist when the core is not there. Well, yeah, but you just took all the stuff that could be magnetized out. So obviously you have very little magnetism. You have very little force by comparison. And also it's the difference, as I pointed out, between I mean, you have to understand, you have to first convert the core into a magnet. But, the simple, it was in the last video, so I shouldn't really do it again, but it's a huge difference. So if I have a coil, and you put the piece of metal inside the core. So the point is inside the core, the coil it's creating a reflective surface. The electricity going through is creating a reflective surface, so the energy is bouncing back and forth inside the coil. Point is, when I put the metal in, okay, then what I'm doing is I'm creating a mirror surface on the metal, and so now the reflections are happening in this tiny amount of space. So it's the ping pong ball paddle thing. If I have a ball bouncing between two paddles, if I put the paddles twice as close together, I get twice as much energy. Obviously, in this relationship, you're putting them a lot closer than twice as close. So you're going to create a lot of interactions, and it's interactions that are energy. That's the transfer. The interaction is the transfer. More transfers, essentially more changes. All right, let's see. Think about it. The magnetic field in this iron, the iron. So again, there's no field in the iron. It's either a light bulb or not a light bulb. It never cuts the conductor. Well, it's clearly hitting it. It's clearly creating it. So another nonsense. If the field exists, it's obviously cutting it. The point isn't so much about cutting a field. The point is, again, you have to make a mirror before you have a mirror. So you have a bunch of atoms here, and all you're doing is sending the energy through one path, or this path. You're not making too many magnets, right? So the way you make a magnet is to send energy through them, is to have the energy move through the atoms. So that's how you magnetize them. And you have to have them line up, so you have to send the energy in the right directions to have them all polarize in the same direction. That is, have all the magnets go the same way. If the magnets go a different way, well, that's going to screw up your magnetic effect. It's going to cancel it out. So the idea is to have all the little atoms get changed in all the same direction. And you do that by motion. Motion in, see, because it's like a light bulb. It's shining this way. It's hitting certain spots. And you want to hit more spots, then you move it. And it'll hit more spots. And that means you're creating more currents, more little eddies, more whatever you want to call them, but more transfers of pressure from the surface to the interior. More transfers, more transfers, more transfers, more transfers. The more magnets you're making, the more magnetism you're creating. Yet somehow the conductor still develops EMF. So again, in an air core. Yeah, and it does it much less effectively because you don't have a magnet connecting the two coils. So you want to make a really shitty transformer, that's how you do it. You don't have a core. Sure, magnetic lines go everywhere in the toroidal shape. So where's the evidence of that? No evidence whatsoever of any toroid or anything moving in a toroidal shape or doing anything to cut anything. So just complete nonsense. No evidence of your toroid. So by your definition, I could make a transformer and just with a magnet and just stick the magnet here and let the tornado do a bunch of cutting of lines. Nobody's invented that. It's never worked anywhere. So it's just more crap. Let's see, and cut the conductor, but the iron. Okay, and cut the conductor, period. But the iron is a new sentence. Okay. It's there to confine the field. No, it's there to amplify the number of interactions. It's there to create a stronger mirror. It's there to trap. It's there to force proximity, essentially. It's creating less distance between the interactors. And that less distance means you're magnifying the amount of energy by proximity, which is just a fact of the real mechanics of the universe. Hold a piece of steel next to it, it's not magnetic except for the leakage at the edge. We'll see again, hold a piece of steel next to it, it's not magnetic. But it is. That's what the transformer demonstrates, is that there's currents flowing through the steel, and they're created by it being pressurized on the surface. Now, the point is, it's not the kind of magnetism that you're going to detect. It's not elemental to the function. What's elemental is the fact that there's currents. Alright, it's not magnetic except for the leakage at the edge and the joints between the E's and the Is. The E's and the I's. Joints between E's and I's. Currents and energy? I don't know. That doesn't... Who cares? Referring to Steinmetz, which, again, what's the point? So why don't you quote Steinmetz? Most of Steinmetz is a bunch of equations. Unsolvable equations. And Faraday. Okay, so go ahead, quote Faraday. That seems like something in a reasonable park. And knowing that the electric field is also outside the conductor explains it. So, of course, the field, the energy, goes outside and transmits to another object at the speed of light. Because that's what it is. It's just like light. It's energy that goes from the light bulb to some other surface, and it travels there at a speed. Shit. Okay, the magnetic flux, again, the rays of light, okay, that's what flux is, rays of light, is interacting with the potential electric field. So we don't even have an electric field, we have some sort of potential electric field, whatever the fuck that is. No, it's radiating energy. Surrounding the conductor. So again, no, it's just about changing distances. It never cuts the conductor. So of course it creates more energy as you move something. You cause it to spread more. So if I'm painting or anything else and I move the spray painter in and out, I get a more even surface than if I hold the can in one place and shoot it. Just a fact. So as I move it, I'm changing the angles where the stuff is hitting. Not really changing the angles, I'm changing the distance, which means the angles are creating a different location. So same angles, new location. So now I'm creating more eddy currents, essentially. I'm creating more places where I've hit an atom and it's causing a chain reaction in those atoms that are creating polarized atoms. So I'm creating magnets, more and more and more of them, and that makes the surface more and more reflective. That means I trap more of the paint between us. It's a chain reaction, it's an interaction that amplifies the effect over time, and that's why movement's essential. Alright. I mean, the laser beam example isn't a very good analogy, but the point is you could sort of understand that for a laser beam to be, if a laser beam was creating an image, was burning a surface, and when it burned the surface, it made it into a mirror. You could sort of understand that if I hold the laser beam in one place, I'm not going to make much of a mirror. Alright, I'm not going to have much of an interaction because I haven't changed very many of the atoms. I've only changed that one. I keep hitting that same one. It's already changed. But if I move the laser around and around and around, I start mirroring the entire surface. It's not a perfect analogy, but whatever. As per Faraday, there are no fields inside a conductor. It's really pointless to talk about fields, okay? The point of the whole electricity thing is not that it's creating a field, it's that it's creating magnets. It's polarizing atoms. So the conductor, when it's conducting pressure, it's polarizing atoms. And it's the polarization of the atoms that is creating the side effect of creating magnetic filters, you want to call them. It's mirroring, it's creating mirror. So the more, again, as you move electricity between atoms, you cause the atoms to become mirrors. Alright. It's all on the outside, so it really isn't all on the outside, so that's sort of a lie. It's just the difference is a million times difference between the strength of the field inside an iron core coil and outside the coil. Because there's nothing to reflect the energy on the outside. There's no mirror on the outside. So there's no way for any of the energy to get trapped or for the paddles to move closer. There's no paddle to reflect the energy. All the reflections happen on the inside. It's that simple, idiot. Okay, everyone explaining how a transformer works chooses to ignore the bit of black magic, There's no black magic where the magnetic field somehow induces an EMF in the secondary without cutting the conductor. So again, it has nothing to do with cutting something. It just has something to do with moving. You have to spread the energy, or you don't create enough magnets. You don't create enough mirror. It is the Faraday paradox conveniently ignored. So there's no Faraday paradox beyond the fact that they've taken some of this too explicitly. Again, Faraday is wrong. Okay, you're not cutting lines of force. You're not cutting, like say a magnet creates these lines on the outside. You're not cutting those lines. There's no lines in reality. There's no such thing. What you're doing is changing how many atoms you're exposing to a force by moving the field. So as you move it, you change the number of atoms you're hitting. And because the conductor takes time to change, see, there's no point in keep hitting the same location. It just doesn't get you anywhere. Your job is to create as much mirror as possible. Hitting the same spot will not do the job. So you have to move it to create more of it. It's that simple principle. So there's no, this whole thing comes about when you spin a magnet on its pole. And, in theory, there's a bunch of lines coming out of there, and they're supposed to be cutting all those lines. Well, they're not really lines in the first place. They're rays of energy. So it's just your misunderstanding, dumbass. I mean, all this arrogant crap in defense of a garbage theory, toroids and hyperboloids and all this crap that you can't prove any of it exists. You can't find a single shred of evidence indicating magnets doing anything active. Okay, like there's a whole bunch of swirly crap that somehow has an endless supply of swirly crap. There's just no evidence. So you have to sort of understand that all it really is a mirror. You can turn it on, turn it off. And all it can do is reflect energy coming from some other source. Just like the earth and the sun and everything else. Energy has to go in for energy to come out. You're not smart enough to figure that out? Or else it has to burn something again. Alright? The sun doesn't burn anything to make gravity. So clearly it burns something to make photons. There's a huge difference. You can understand that difference. One kind of energy has to be something that went in to come out. The other energy is clearly just burning stored energy in the sense of having mass and atoms to break. It's breaking atoms. Alright, anyway. Well, combining atoms. Same difference. So anyway, yeah, fuck you. No quotes of any kind, no, like again, all this crap. Conventional science says, no evidence that that's what they say. I mean, it's just such crap as an argument, just absolute crap. I'll just remove it for now. See, give you another shot to be human, decent. No, not to be human. Do a little better than generic butthole talking out of his ass. Try making an intelligent argument. One with some sort of facts and detail. So anyway, so off to drag, I suppose. So that will require some drawing and such, and so forth and whatnot. Probably. So maybe I'll take a little break. Maybe I'll try to take it this way. I should be back. Yeah, I should be back. So anyway, this little bit of universe, okay, the idea is that the universe is full of energy, that there are a bunch of photons that aren't in a form that we can see. We can only see big ones, long rays, lots of little rays in the universe, lots of rays with higher frequencies, lots of energy flying around all the time. So like if all the other energy could be seen, like visible light, we're in a lot of brightness, very bright world. And where we cast shadows, we essentially cast radiation, where there's a lack of it, and the radiation is essentially movement. It's essentially a push universe, and things can shield each other from the universe. That is, this part of the universe doesn't get to there because it slowly moves this thing by getting trapped in here, And then this thing doesn't get hit with energy here, it's not there, so the energy over here becomes more powerful, moves this thing this way, and vice versa, and just keeps going like that. And that's basically what fuels the interactions of large matter in the universe. That's why it's moving. That's why there's gravity, and there's magnetism, charge. That's the phenomenon, essentially. So you just follow the movement. So it's all what we reflect. It's all what we take in energy and we give it back in a slightly different form. And that's all this is about. You could argue that it's like what I explained the other day in terms of the sun will take in a piece of energy, a piece of momentum in this direction, and it'll give it back by giving it motion in this direction or this direction or this direction. Anything on this 180-degree plane, in both dimensions, it can give back what it got in this direction, because all of these arrows have a component the same as this, and that component will count as the conservation, giving it back. So yeah, I'll have to give back 2 of those, like 2 of these to equal 1 of these, but the point is that's the form it'll give it back in, is in moving this way and then moving that way, and it's essentially given back this way. Okay, so that's the way it works. So something specific goes in and something mixed comes out, but the thing that's consistent is the direction. So the directional momentum is conserved. Anyway, so there's this subject. So if you have this particle drag, this particle idea of force, this idea that force is in little clumps, the little clumps interact with something and exchange their momentum, blah, 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 blah. Then you have the issue of drag, which is basically just saying when you're standing still, the forces are all equal, but if you start to move, okay, you move this object, well, that means it's going to move into more stuff this way and less stuff this way. And so somehow it's going to have more interactions forward than it's going to have coming from behind it, and therefore it's going to be dragged to a halt eventually. It's going to lose its velocity. Yet we don't see that happen with large material objects. They don't seem to drag. Now the small ones, like electrons and protons, do seem to just drag to a halt. They just stop and spiral into something. They drag down. We can't make real electron guns. Can't make a real proton gun. Can only do it when we create a special environment for them to fly through. A special environment that keeps pushing them. Okay, if we don't keep pushing them, they don't keep moving. So we have to keep hitting them with force to keep them moving. And if we stop hitting them, they stop moving. All right, so anyway, so that's a very brief description of the problem. So let's imagine a thought experiment, because frankly I can't make electrons and protons, and I can't make a speed of light force that never slows down or never loses momentum. So I can't make these things, so I can't make a real experiment. Now I could simulate it in space a little bit, but it won't work, okay, with material objects because they aren't the same as the force. So anyway, so the idea would be, it's like I'm imagining Einstein's light clock. The idea is you get a photon inside of a container, and then the container becomes a mirror, and it just, so however you get it in there, let's say you just emit it from inside, and then the emitter disappears. But the point is I throw essentially momentum into a box, okay, and you can think about the box on wheels, I really don't care, or you think about it in empty space. The idea is I'm throwing something that has a perpetual momentum. So let's understand the speed of this thing never changes. Okay, it's always the same. It never changes, and that's what a photon is. It doesn't change its speed. And so what this does is it'll hit this wall. Okay, and it's going to make an exchange by my philosophy, but just say you can see the obvious. It's going to exchange the momentum. And you would think, okay, and then the photon stops. Well, we know photons don't stop, right? You know that's not what it's going to do. So imagine that it reflects, okay? Well, the point is that it gave this thing momentum. So this whole car is now going to move this way, all right? because something hit it. And the thing that hit it, okay, it made an exchange is the point, right? My argument is what electrons are doing, this is the rule, is something goes in and something comes out. Okay, it changes, it has stored in it event, and what it does is this event exchanges for one of the previous events. So it's just an exchange, perfectly conservative. So it just gives back something. You give it a frog, it gives you a turtle. You know, that kind of thing. It just stores stuff and then it gives back. So a new bird flies into the cage, I let one of the birds out of the cage. So I always have the same number of birds in the cage. So that's a simple added background. See, the mechanics is very much like the physical mechanics in that you could understand that if you threw a bowling ball into a wagon, that the wagon would move in the direction of the bowling ball, right? And then, you know, that whatever would happen, it would happen going that way. There wouldn't be any energy going this way. But so for the sake of the argument, though, this has to be understood because we're going to use these two things are connected. So these two surfaces are connected. So when this thing hits, it moves the cart. The cart moves to a new location. Well, the consequence of moving to the new location is now when this reflection comes back, this distance is shorter. See, this is the old distance it would have had to travel, and the new distance is this shorter distance. Because now when I hit it here, this is where I hit it, right? I'm not going to go all the way back to that distance. I'm only going to go this shorter distance before I reflect. And what happens when it goes back? So what happens when the photon reflects and goes to this other surface? Well, it doesn't make motion that way. This thing's already moving. So it just takes away, and it's always the same energy, the photon. So let's understand, it's applying the same energy it hit here with, it's going to hit the other side with. So this thing is moving that way, and now you hit it. Well, now it stops. That's all it does. It just stops. Okay, and now the photon's going to go the other way. All right, it's just going to take time to get there, whatever amount of time, blah, blah, blah. And the whole time, this box is now stopped. And so what's going to happen is, again, we're just going to redo the first event. So that is from this position, we're going to basically hit it here again, right? And now we're going to make the exchange. Now the cart's going to move. It's going to move to this new location. And the new location, the surface is closer. So this one travels less distance. And it's moving while this is going this way. So let's understand the movement. The movement of the cart this way always happens while the photon is going this way. Right? That's the key to it. The cart's moving this way while the photon's moving that way. When the photon's moving this way, the cart's not moving. Okay? So that's the catch. All right? And that's all the catch you need to essentially overcome drag. Because the interesting fact is, let's say I was dragging. So when the cart's moving, I hit it with extra force in front and I slow it down. Well, what's the consequence of slowing it down? Well, if I slow it down, that means it doesn't move this surface as far. So this surface isn't moving this way. It's not getting closer to the photon. So the cart keeps moving longer. That's the catch, right? So the more I slow the cart down, the longer it takes this photon to get to this surface. This surface is where the stop happens. There's no stop without it hitting this without it hitting this surface. It doesn't stop until it hits this surface. So if this surface slows down because of drag, well, then it's not going to stop where, in the same amount of time. So that means the cart's going to roll further. It's going slower, but it's going to roll, keep rolling. So it's still rolling for a longer period of time. And that's the thing that overcomes the drag, because the more you slow it down, the longer it takes the photon to get to the back surface. That means the longer you're rolling. So you're changing the time portion of the equation, okay, by changing the velocity of the cart. So if I lower the velocity of the cart, I make the cart roll longer. So those two are now inversely related. And so I can't lose velocity. I can't lose any energy because the energy is really in this interaction with the photon. That's the momentum exchange. So what I'm saying is if you did this thought experiment in space or someplace, the thing would move in spurts. It would move and then stop for a period of time, and then move and then stop and then move and stop, and it would always move in one direction. So the energy going in, the initial energy, defines the motion, and it will be in that direction. It just won't happen all at once because the energy is being converted through this process of interaction. So if I were to attempt to draw it in some way, the idea is the motion is something like this, and then there's a time back, and then there's motion forward, and then there's a time back, and then there's motion forward, and there's a time back. And you can sort of understand that if I lengthen the amount of time back, I'm increasing the amount of motion forward. So it can't be you can't harm the event by slowing the cart down, because every bit I slow the cart down means I'm extending the amount of time. Okay, this has to move forward, because it only moves forward while this is going backward. So while it's stopped, see, this is really stopped. I'm saying this is the photon's motion. When the photon's moving this way, the cart's moving that way. So again, you can sort of understand that if I lengthen the amount of time the cart's rolling, I'm lengthening the amount of time it's moving forward. I'm making it go further. And it doesn't go further. I'm not saying you make extra energy. I'm just saying it completely compensates for the change in the velocity is proportional, okay, to the change in time. And the more time you're adding, even at a slower velocity. So more time. So as time goes up, velocity can go down. So that you could understand as a simple equation, right? So if my velocity goes down and my time increases, I could cover exactly the same distance. So I could have an amount of distance that you have to cover, and I can cover it if I increase my velocity and shorten the time, or if I lengthen the time and shorten the velocity, I can do the same distance by just changing one of those two numbers. And they're exactly what's getting exchanged in the drag argument. So the point is you can sort of imagine this thing in space, and that the cart would just jerk its way forward, and you couldn't change the fact that it's going to cover a certain amount of distance in a certain amount of time, because its velocity is inversely tied to time. So more time means more distance, less velocity means less distance, and the two will be completely equal because of this fact that you're increasing the travel time as you increase the amount of time it takes to stop the cart. So I think this is an indestructible thought experiment by these rules, of course. Now, see, if I did this with a steel ball, you could sort of understand that the steel ball will hit here, and then the ball stops. Photons don't stop. So the steel ball stops here. The cart will start to move. Well, the back end of the cart will finally hit the steel ball, but if I slow it down, I give the steel ball less momentum forward. So if the cart got slowed down, then when this back end hits the steel ball won't go this way as fast. So with each, it'll rock for a while. I mean, it'll go forward. So you can imagine, you throw a steel ball into a cart, and the ball is like a cue ball on a pool table. It gives all of its energy to the front of the cart, and then gives all of its energy to the back of the cart. You can sort of understand the start and stop thing. But the fact is that as the momentum gets degraded, the velocity of the ball also gets degraded, and so it doesn't give, the next hit will be weaker, and then weaker and weaker and weaker, and eventually the cart will stop. But for a little while it'll go. So you can understand, if it's very low friction, I can throw the energy in and it'll do exactly what I'm pointing out, but it'll lose energy because the ball isn't an indestructible force. Okay, so it's not a photon, and that's the difference. So that sort of solves the drag issue. So this is a draft. I'm not making this my final statement on drag, but I'm just pointing out that you can overcome drag by something as simple as the trap I was talking about. So I've been talking about traps that could be 4 directions, arrows in 4 directions, that's a trap. Cul-de-sac, a circle is a trap. But in fact, okay, just 2 surfaces is a trap. If I can get inside of there, it's trapped. And that trap overcomes drag. Alright, I think that's probably enough on that. So the other thing I was thinking about, might as well throw in a bonus. Another, basically the 2 slit experiment's really important stuff, this whole light diffraction thing, and I've sort of pointed out that the single slit in water, no luck, no interference. Okay, no interference. Double slit. Let's put it this way. You gotta have interference, okay, but you have 2 patterns. All right, you got 2 patterns superimposed on each other. So water doesn't do that. So it doesn't completely match water. Matches water by 1/2. 1/2 match to water. Multi-slit, diffraction gradient, images to the locations, exact images of what goes in. So whatever goes in, an image of it goes to the locations. No way that wave interference is going to make images go here. You can't randomize the behavior of the photons and have the image accurately sent. So I'll put a little cross on it just so you know. It's an image. The image can't go places if you've randomized the interaction and caused destructive anything. So anything destructive would destroy the images. So there really isn't any match. This doesn't match water. This doesn't match water. And this only half matches water. Very little evidence for you to conclude it's just like water. No, it's not just like water at all. Alright, so the interesting feature, I'd say, so this is again pretty draft. Nobody ever talks about the single surface. So the idea is that if you put a single surface, here's a surface, alright, and here's your beam of light, what happens? Okay, so the argument is people say, well, a lot of people, nothing. There's no diffraction, but there actually is. The problem is that it's in the direction, okay, not of the shadow. So here's what it projects, right? It projects a shadow over here, so it's dark here, all right, and it's light over here, right? And so that's what it's going to project. But the problem is it's doing the diffraction, that is the light. I'm going to argue that the light here, photons as they go out, the ones that are right close to the surface have the strongest deflection, and then the ones further, less deflection, further, less deflection. So the further out you go, the less deflection there is. So the light that's out here, the photons out here go pretty much straight. And then you have a lot of deflection on the ones closer. So the closer you go, that means the closer you are to the surface, more likely you are to hit an electron. If you hit an electron, you're going to get a change in your momentum. This electron's going to move and then move back. And when it moves back, it's going to reemit the photon. So the problem with the single surface pattern is, first, there's nothing pressurizing the surface. That is, you don't have another surface encroaching, so you're not compressing the electrons. But the other problem is you're shooting the pattern into the side where all the light is going. So you just don't see it. Okay, it's there, but you just don't see it because it's so overwhelmed by the number of photons that aren't anywhere near the surface. So it's sort of overwhelmed out of visibility. But it's there. And so then you have the single slit. And so what's happening there? Well, by what I'm saying is that it's not how you think, like this one's bending around and going this way, and this one's bending around and going that way. That's not happening. It's exactly the opposite's happening. This side is creating this pattern, and this side is creating this pattern way over there, and then the stuff going down the middle is going right down the middle. All right, so that's how the pattern's being created. And then if I use the single impediment, you know, the same kind of thing is happening. Is the light's not bending around, the light is bending in, away from the surface. So this side is making this side, right? Well, and obviously the closer you are to the surface, the further the line goes out, and so forth. And this one's doing that opposite. All right, so then you can see then when you blend two slits, all right, that I'm not going to draw it all, but the two overlap, the two cross over each other. So these two surfaces create this stuff, these two surfaces create the stuff on this side, in terms of the pattern change. And it just has to do with how close the photon goes to the surface. So the closer it is to the surface, the more likely it is to be way out here. The further from the surface, the more likely it is to be in the center. And that's all it's about. That's all that's creating the pattern. So, something to be understood. See, they don't have a theory for this single surface pattern, but it is there. I mean, they do detect it. It is there. It's not some fact I'm making up. There is a pattern created by a single surface. It's just not as strong. It's not as isolatable because you're not blocking enough of the light. Okay, I mean, that's what it comes down to. With all these other slit experiments, you're blocking, you know, more of the light that's going to be, that you're viewing. So you're viewing the pattern in shadow. Okay, and that's really important. If you're viewing the pattern in the shadow, see, especially with this one, you can see you're viewing the pattern. Well, it's not really in the shadow, but you've created a shadow right in the middle, so you've blocked the strongest light. So that's why this one works, is you've blocked out the strongest light, and you're only dealing with the fringe light. But it's really just has to do with, you can't see the light very well if you're trying to see it where there's a whole bunch of light hitting, and it just, the intensity of that light completely makes the little thing invisible. It's like a small shadow can't be seen, right? I can take an object and I can make its shadow irrelevant, so you don't see it because the light intensity isn't substantial enough. I mean, there's too much light hitting the surface for you to see the shadow of something from a distance. I suppose I could illustrate, well, I can't really illustrate that great, but the shadow gets much weaker the closer I bring it to the light, and it almost disappears as a shadow because it's being dispersed. It's being spread over more and more distance. The closer I get to that object, the bigger I'm making it, and therefore the less intensity it has because it's spread over more surface. And so that's part of understanding all this crap. So that's probably enough of a video. Yeah, it's getting kind of yeah, the frames are getting kind of stalled, so I'm probably best to stop here. So anyway, till the next time and such, so forth and whatnot. Yeah, that's enough.